We are going to talk about Vesper theory and molecular geometries. Again, Lewis structures are the most important thing to be able to discuss. Once you get the Lewis structure down, then you can relate to the table. Now, the structure of the compound determines their properties. And that would be looking at polarity overall. It would be looking at the shape of the molecule. And that's what bonding theory predicts, the shapes of the molecules. Valence shell electron pair repulsion theory, Vesper theory. It identifies that when we have a central atom and we have some bonding occurring, what we'll call electron groups, we need to give them as much space as possible. We know electrons repel. And so if electrons are getting close together, they're gonna start repelling each other, and that's not good. We don't like repulsions, we like attractions, right? We wanna just keep this attraction going and not the repulsion. So when we have things like two electron groups, what we'll see is that they want to be spaced out as far as possible. Two electron groups would be what we call a linear geometry. Very important example, CO2. Those two electron groups are oxygens, 1, 2, around the central atom. They like to be spread out 180 degrees. Now, our incomplete octet with boron is a very important example of the trigonal planar geometry, the 3 electron groups. Again, the 3 electron groups being 1, 2, 3 outer atoms. Boron will make those outer fluorines equidistant from each other, which is 120 degrees. Now, CH4, our 4 electron group example, looks at carbon in the center and says, yes, if there are 4 hydrogens all around him, we're not going to be planar anymore. We're not going to be flat. What we actually pop into is a tetrahedral geometry. Now think about these 3 on the bottom, these 3 hydrogens being similar to a triangle with 1 flagpole at the top, right? So it's changing into what the tetrahedral comes from, is the tetrahedral crystalline structure that we would be mirroring this idea off of. Now, a domain is the same thing as an electron group. I like to think about it as things around the central atom. For 5 and 6 electron domains, we have a much different structure because of the expanded octet idea here. What we start to see is equatorial positions, things around the middle, the equator. Same thing over here on the 6 group, versus the axial positions, our flagpoles here, up and down. These structures you do not have to draw. They would just be being able to look at a Lewis structure and identify how many things around that central atom, and so which shape do we go into. All of these shapes have different bond angles and different names, so be very careful with their names. I'll show you the overall chart in your textbook in just a little bit. Now, lone pairs count as a group. Even though you can't see them, a lone pair is already going to be in a specific position. It takes up space. So when you think about NH3 and H2O, if you were to draw that Lewis structure, you'd see that there are lone pairs. Now there is a slight distortion of the bond angles. We see that these are less than 109.5, the normal 4-domain system for the tetrahedral, but they still have that tetrahedral geometry. What we think about instead of these is giving them a couple of specific names to identify that the electron groups, some of them are bonding and some of them are non-bonding. Same thing for the trigonal bipyramidal electron geometry, we don't put that lone pair in an axial position because of the pair bonding repulsions. We would put it in an equatorial position only. And again, even though they might look like, oh, they're invisible, they're just there on the sulfur, they actually do take up shape. So make sure you imagine that shape counts the lone pair. We'll practice with VSEPR theory a lot together in class. That will also be our way of practicing with Lewis structures. You can have 2 lone pairs in that 5 electron geometry count. You can have 6 lone electrons or 3 lone pairs. This again is a good example of, yep, that's a noble gas. We can get it to react. Don't be so surprised. We'll go through all of these VSEPR theory molecules in class together. The 6 electron geometry system could have 1 lone pair or 2. You can place that 1 lone pair anywhere, axial or equatorial. It doesn't matter because of the 90-degree bond angles all around. However, when you put the second one on there, they have to be on opposite sides in order to reduce the electron repulsion. Here is the overall chart that's really important for us to be able to look at. When you're looking at this chart, you start reading over on the left-hand side and identify just how many things total around that central atom. Then you would want to say how many are bonding versus how many are lone pairs, and then determine the electron geometry and the molecular geometry. We will focus on the molecular. These are the specific names based off of how many bonding versus lone pairs, non-bonding electron groups we have. These are very important to know. Approximate bond angles are very important. Again, you'll see instead of the 107 and the 104.5, we'll just say less than 109.5 when you start getting lone pairs. That's a-okay with me. I don't need the specific number for the molecular geometry, but the general number you see here in this column is going to be important for us. Again, you do not need to know how to draw. Know only the molecular geometries and the bond angle. Those would be the most important. You do not need to learn how to draw these in 3-dimensional shapes. The Lewis structure will suffice. These guys are a-okay for us to keep. So don't worry about doing any of this 3-dimensional colored format of the ball and stick models. So overall, to use this chart to be able to predict the structure and the shape, you would need to draw the Lewis structure, count up the number of things around the central atom, classify each one of those things as bonds or lone pairs, and then refer to the table. Remember, multiple bonds just count as one group. What we saw in carbon dioxide, even though carbon to oxygen is a double bond, it's still just one group over here and one group over there. So 2 electron groups, they are bonding. Great. When we start looking at these illustrations, this is in your textbook where we have what we call a wedge and dash format. You do not need to know how to draw these. We will practice these in organic chemistry. I look forward to that day, and today is not that day. Now, for a molecule, once we've seen our structure, once we've done the Lewis, once we've done the actual VSEPR theory 3-dimensional shape, we can start to think about the polarity of the molecule, taking what Linus Pauling taught us and relating it now to a molecule itself. Here's the take-home message. If you have a polar bond That's the first step. You need to identify, do I have at least one polar bond? And then, do I have an unsymmetrical shape? That will give you a polar molecule. Now, symmetry negates all of the idea of bond polarity, because if you're a perfectly symmetrical shape, you have vector addition and those vectors cancel. If you are unsymmetrical, so say you have different types of bonds, doubles, triples, singles, or you have one to oxygen and one to fluorine and one to hydrogen, differences make vector addition result in a polarity of the molecule itself. Non-bonding pairs, lone pairs, do not affect molecular polarity in terms of they are not polar themselves. However, they create that unsymmetrical shape. So if you have lone pairs and you have a polar bond somewhere in that molecule, you must have a polar molecule. And a typical example is HCl. These binary molecules between just two atoms are a good representation of asymmetry. Hydrogen and chlorine. Chlorine is the delta minus, hydrogen is the delta plus. We have a polar molecule. Another example of a little bit bigger molecule that had a polar bond but is symmetrical is carbon dioxide. Yes, in terms of polarity, oxygen is delta minus, carbon is delta plus, and this guy is delta minus. But because of this perfect 180 degrees linear structure, our vectors for our polar bonds cancel each other out. So the overall net result, a non-polar molecule. There's symmetry at work. Now, water. H2O, if we were to do the Lewis structure, we'd start to see that there are 4 electron groups. There are 2 bonding and 2 lone pairs or non-bonding. And so that would be the tetrahedral geometry, but what we call bent. The lone pairs, if we want to imagine, they're up here. They take up shape. So imagine them taking up space right there. But what that creates is a vector addition problem, where our 2 vectors here are both pointing up towards the oxygen. The overall sum for the polarity of the molecule is that middle portion. What does that mean for us? This area down here is the delta plus. The area up at the oxygen lone pairs is the delta minus. So we can start to see polarity in the molecule based off of its 3-dimensional shape. If you need any help with vector addition, there is a good section in your textbook that talks about vector addition, when vectors are going the same way or opposite ways, if they're equal in magnitude or not. Take a look at that. If you haven't had calculus, it's taking an average of some vectors. And so if you need help with that, let me know. We can practice in class more. And again, vector addition going in 2 different directions, where you sum them up in the middle, 2 or more dimensions. That would be a good section to review if you haven't done any vector addition in calculus yet. Molecular polarity affects water solubility. This is something that we're going to see in general chemistry 2nd semester. Water is polar, therefore other polar molecules are going to be able to react with water, and ionic compounds are great to react here because of this charged nature of the molecule. And so that's where I'll leave you today. When we look at molecular polarity, it's really building up from the idea of Linus Pauling all the way back in determining, do I have a polar bond itself, through Lewis structures, through VSEPR theory, ending with what does my structure look like in 3-dimensional space, and how does my structure overall affect the polarity of the molecule. Thank you very much for joining me. As we dive into chapter 6 here, we'll see our second chapter on chemical bonding. A couple of new theories that we'll see in this chapter is valence bond theory. We'll discuss the pros and cons with Lewis structures and the pros and cons with VSEPR theory. And then molecular orbital theory, which is our final theory on bonding. This is one that is the most difficult to grasp. We won't do too much in depth with molecular orbital theory. You'll do a lot more in later chemistry classes, such as organic chemistry. Our primary focus in this chapter will be looking at the pros and cons of all of these theories and how do they fit together to see a holistic view of chemical bonding. Now, where have we come from? Well, the first thing that we talked about in this class is quantum mechanics, and we've mapped out where the electrons are, specifically looking at the electron cloud and being able to say it's not just a swarming mess of electrons, there's a structure to it. There's orbitals. We had N, L, ML, and MS to be able to write out our electron configurations, fill up that orbital diagram, and we could see where the electrons were in the basic atom. Now, with bonding theory, we started to talk about the different types of electron behaviors, things like electron transfers to make ionic bonds, and electron sharing to make covalent bonds. What's great about this is it was very black and white. We said a metal and a nonmetal transfer electrons from the metal to the nonmetal, make ions, there's your electrostatic attraction. Covalent bonds we also talked about as being between two nonmetals, and they share electrons. All of those are driving to reach a noble gas electron configuration, which is stabilizing. With Lewis theory, when we talked about Lewis atoms and when we talked about Lewis structures, it's a very simplistic view of the connections for ionic and covalent bonds. It tells you who's connected to who and how are they basically connected, single bond, double bond, triple bond, things like that. Again, focusing on valence electrons as they are the electrons that go into reactivity, ignoring the core electrons. With VSEPR theory, what we just talked about was how do molecules look in three-dimensional space? When we want to look at VSEPR theory, what we're really trying to do is give the electrons the most amount of space that they can have in a three-dimensional model. We know that electrons repel each other, but they are attracted to nuclei. And so what we're really trying to focus on are those electron groups in VSEPR theory. Now, with VSEPR theory, there is a little bit of utilizing the chart. We can call it memorization if you want to be able to discern if I have 4 electron groups, oh, that must be a tetrahedral. But the real reason to why hasn't been understood until we get into valence bond theory. And that's where we're going to start. What happened to those atomic orbitals way up here in quantum mechanics? When we talk about these atomic orbitals, they don't just disappear when we make a molecule. And so that's where valence bond theory steps in. There are some issues with VSEPR theory, and that's what we're going to talk about now. First, we'll talk about the problems with Lewis theory. Lewis theory generally predicts the trends and properties, but it does not give a good numerical prediction such as bond length and bond strength, right? It's a good idea to be able to approximate, but it doesn't always work. Lewis theory gives good first approximation of bond angles in molecules, but cannot be used for the actual angle. Now with Lewis theory, we cannot write just one correct structure for many molecules where resonance is important. And Lewis theory also doesn't predict the correct magnetic behavior for molecules. For example, in real life, oxygen is paramagnetic, even though when we look at a Lewis structure, it would predict it was diamagnetic. Everything is paired. Oxygen has its complete octet for both. And so what we really need, and in this Lewis theory, we are containing the idea of VSEPR. What we really need is something to enhance. Specifically, what I want to be able to talk about is actual bond angles. There's been a disconnect between how did we get the bond angles in VSEPR theory, and how do we even get those when we know bond angles or orbitals exist in the atomic realm as S's, P's, and D's, and F's. So here's a valence bond theory. It focuses its attention on what we call orbital overlap. I want us to think about a Venn diagram. If you've ever seen a Venn diagram, you know that it's two circles coming together and having an overlap. And there's the overlap, right? That is how valence bond theory describes a chemical bond, that we have these electrons in these atomic orbitals, like S's, P's, and D's, and when they come together with another atomic orbital, they produce an overlap. I want us to think about this chart real quick. Energy on the y-axis increasing, and distance between two H atoms increasing on the X. So here we have an H atom and an H atom, and our job is to bring these two together in order to make a molecule, H2. Now, once they start getting closer, we start to see a little overlap. And here is where we see a great amount of overlap, right? Now notice that those nuclei aren't touching, the black dots are not touching, just the general s orbital that the two hydrogens would have contained. Get too close, and what happens to the energy? As we notice this energy path, as those two atoms are getting closer and closer, the energy is decreasing, and that's because of attractive forces. The electrons are attracted to the nuclei. Get too close, and what happens? Repulsion takes over. Electrons start to repel the other electrons. The two nuclei start to repel each other as well. There's what we call the perfect sweet spot right here, where this point, the point of lowest energy, where that point occurs corresponds to the actual bond energy and the bond length. This right here would be the internuclear distance between the two nuclei, or what we called the bond length. And up here is our energy released when the bond was formed, bond energy. It's also the amount of energy required to break the bond. So when we look at revisiting quantum mechanics, bonds between atoms should occur when the orbitals of those atoms interact. They need to overlap. They need to occupy the same exact space. And when they do that overlapping, we have to find the perfect amount of overlap. We can't get too close because then we start to repel. We can't be too far away because then we don't have enough attraction. And the kind of interaction depends whether the orbitals align along an axis or between the nuclei or outside the axis. So what we want to be able to talk about is there are going to be a couple of different types of overlap. This one that looks like a Venn diagram to me is our most straightforward type of overlap. When we want to discuss the different types of overlap, that'll be more geared towards when we're ready to start discussing molecular orbital theory. The first thing that we want to be able to look at is just this basic idea of, well, what type of overlap do I have? What atomic orbitals do my valence electrons reside in? So in valence bond theory, the valence electrons, right, create the bond. There's where we get the name. The valence electrons of the atoms in a molecule reside in a quantum mechanical atomic orbital. These are our s, p, d, and f orbitals. Now, what valence bond theory also brings about is the idea of a hybrid orbital. Some of the shapes that exist based off of our discoveries in VSEPR theory don't make sense for S's, P's, D's, and F's. And so what valence bond theory does is it enhances what we know in the atomic realm and says that there could be a hybrid combination of these atomic orbitals. And a chemical bond results from the overlap of two half-filled orbitals. Again, one electron from each atom need to come together in this bond. So the geometry of the overlapping orbitals is what really determines the shape of the molecule. And this last one is where we really want to focus on. This valence bond theory is enhancing what we see in VSEPR theory. So, basic idea here, orbital diagram for the formation of H2S. Now this is a covalent molecule. S will be in the center because he makes the most number of bonds. We have H then on either side. If we wanted to count up our electrons, we're just doing the Lewis structure right now. Again, everything results from a Lewis structure home. If you're not comfortable with Lewis structures, you will not be comfortable with anything else in chapter 5 or 6. We have 8 electrons total. I'm going to put 2 electrons in the bonds between each hydrogen and sulfur. Then we complete the duets or octets of the outer atoms. Well, they're hydrogens, the duets are done. The other 4 electrons get placed on sulfur as lone pairs or non-bonding electrons. Now, what we can see here is that the 1 electron from hydrogen is going to be paired up with one of the unpaired valence electrons from sulfur. The same thing will go for the other hydrogen. Sulfur has 2 unpaired electrons in p orbitals. So what we can imagine with those p orbitals, there's the p orbital. It's got 1 electron in it. I'll just draw it on that top lobe. Hydrogen is going to come along with its 1s orbital and its 1 electron, and they're going to join together. If we want to imagine what that looks like in a Venn diagram, I'll keep the phases there. There you go. We could put the little electrons in there as well. I know it's a little squishy. Maybe I'll make it a little bit bigger for us. What we see there is the overlap between a hydrogen that was an s orbital and a sulfur in its p orbital. Same thing happens in this type of a diagram. We see that nice Venn diagram idea where each of the half-filled p orbitals starts to overlap with the half-filled s orbital. Now, what we would predict here with this valence bond theory is that the bonds formed are about 90 degrees in H2S. The reason for that is because when we look at the p orbitals, remember the px, the py, and the pz were on that 3D Cartesian plane, all 90 degrees from each other. And so that's where we can get that 90-degree outlook. And this is actually quite true. H2S has a bond angle of around 92 degrees. So it's very, very close. There might be a little bit of electron repulsion there from that last lone pair in the p orbital, but we see that there's a good organization about looking at valence bond theory, how the atomic orbitals overlap with each other. Now, if we were to use Vesper theory here, we might look at this Lewis structure and say that there were 4 electron groups, and that would be the tetrahedral, which would have a bond angle of about 109.5. A little bit less because of the lone pairs, but still around 109.5. Now, which one was better? Well, valence bond theory is actually a little bit better for us here. But what we want to be able to say is it's a marriage between the two that we want to be able to identify. Now, the main concepts with valence bond theory is that valence electrons of the atom in a molecule reside in quantum mechanical orbitals, S's, P's, D's, and F's, right? That's what we just showed. The or now, they may be in a hybrid combination of these. Why do we have Vesper theory where a majority of those 4 electron group models come in a tetrahedral with a 109.5? Where the heck did that 109.5 come from? It just didn't come out of thin air. Something must have constructed it when we see so many different 4 electron group molecules having the same random bond angle. So when we want to start thinking about the hybrid, we're going to have a couple of very important definitions for what a hybrid atomic orbital is defined as. Remember that an atomic orbital here, we might not have used that word for a while, but an atomic orbital is our S, P, D, or F orbital, where the valence electrons lie. So if we're talking about a hybrid atomic orbital, we are merging a couple of different types of plain old atomic orbitals. So I could take a combination of S's and P's and D's, mush them together, and we'll discuss what that means. Now, a chemical bond results when these orbitals interact, and there's a total of 2 electrons. And that becomes a new molecular orbital. This is where we start to see how molecular orbital theory will play a role in valence bond theory. Now, the shape of the molecule is determined by the geometry of those interacting orbitals. That's where Vesper theory, valence shell electron pair repulsion theory, is enhanced. All right. Now, according to valence bond theory, bonding takes place between atoms when there is an overlap. A couple of different overlaps I want to be able to talk about. It could be this direct overlap of atomic orbitals. So here's an s orbital and here's an s orbital. Let's bring them together. And they do a nice little Venn diagram right there. Now, another type of orbital overlap that we could see was with the p orbital and an s orbital. This is not hybrid yet. This is just overlapping of plain old atomic orbitals. We'll overlap that a little bit more. Being aligned along an axis. These would be aligned along an axis, this type of direct overlap. Now, what I like to relate this to is hand holding. The orbitals are literally holding hands. It's just like a relationship, right? Brand spanking new relationship, you want to hold hands. And the other type of overlap is not going to be this along an axis. Instead, what it's going to be is a parallel relationship. And the most typical parallel relationship we have is with our p orbitals, and it's here. This parallel relationship is going to be important for us. Now, when 2 p orbitals align like this, They should have one electron in each, and they should be attracted to each other. But notice how they're not technically touching. I call this a high school relationship. Not holding hands. I know I'm in a relationship with you, but I'm not going to touch you. I know, Lauren's insane. But the parallel relationship is weaker than the axis relationship. And so when we're looking at these two different types of relationship, we will see them come into play in valence bond theory as we start to describe Lewis theory, VSEPR theory, and how the overlap occurs. So just note there are a couple of different ways that the orbitals can align. These are going to be our two main ways. We will call this that's aligned along an axis, we'll call that a sigma bond. A sigma bond is always going to be a very strong bond. It's that direct overlap. Here, I'll change the color so that it's back to the purple. It's that direct overlap of atomic orbitals, sigma. Also abbreviated with the Greek symbol sigma. The parallel relationship is going to be called a pi bond. It's abbreviated again, pi, just like the Greek symbol pi. We'll start to look at these orbitals and see how they come into play and when to be able to recognize them once we start drawing our 3D shapes again. All right, so what happens if we do not have the correct number of unpaired electrons? Here's an issue. I want us to remember carbon's electron configuration. I know that was a long, long time ago. Carbon, for its orbital diagram, valence orbital diagram, we're only going to do the valence, remember, because those are the ones that are go into reactivity, go into bonding. Its valence looks like this: 2s2, 2p2. There's one electron in the 2px and one in the 2py. Now, how can we look at this quantum mechanical model of carbon atom and see any relationship into VSEPR theory where carbon can make 2 or 3 or 4 bonds? When it makes 3 bonds, they're around 120. If we had 4 bonds, that's 109.5. What's happening? Because we know in reality, these are 90 degrees from each other, right? What we just talked about with sulfur. What happens is a hybridization. Now, because of the inconsistencies when we started viewing atoms and seeing the shapes that were occurring, VSEPR theory was born. But then what happened was people and scientists were really baffled by the inconsistencies. And so it was postulated that valence atomic orbitals could hybridize before bonding took place. And so one hybridization of carbon is to mix the s's and the p orbitals. And what happens when we mix s's and p orbitals, even though these are all different energies, let's imagine throwing them all together, putting them into 4 equal energy orbitals, and 1 valence electron goes in each. What I like to compare this to is cupcakes. I hope we've all made cupcakes before. I hope we've been that lucky in our life to have made cupcakes, or at least seen cupcakes, maybe eaten a cupcake before. Now, cupcakes are made with sugar, flour, eggs, some sort of liquid, whether it's oil or water or butter. And we mix all of those very different things together. And when we mix them all together and we put them in equal little trays, we hybridize those ingredients. We are literally taking very different substances, mixing them all together to make perfect identical cupcakes, hopefully perfectly identical. Now, that's hybridization. We take different atomic orbitals, mush them all together to come out with degenerate orbitals. Now, if we remember what the word degenerate means, Degenerate means equal in energy. We are trying to make equal little cupcake orbitals for our central atoms. Now, when we look at this, what we want to be able to see is carbon does not bond as theorized with valence bond theory originally, or quantum mechanics. What it actually does is a tetrahedral when we have single bonds. So something must be happening to these valence electrons in order to get them to separate. We got to unpair and become equal in energy. All 4 of those bonds in CH4 are the same in terms of bond energy. And so something must happen to those atomic orbitals. And that is what we call hybridization. Hybridizing is mixing different orbital types to get a new set of degenerate orbitals. Now we can mix S's and P's and D's. Hybridization has not been noticed past those D orbitals, but notice here that there are a wide variety of combinations. Sp contains one S orbital and one P orbital. Now that 1 is not the principal quantum number, we're talking physical orbitals that we've taken. Sp2 would be an S orbital and 2 P's. Sp3 is an S and 3 P's. Sp3d, you grab one more D. Sp3d2, you grab 2 D's instead of just 1. Carbon can bond in any of these 3 ways. It can be Sp, Sp2, or Sp3 hybridized. And that's what we're going to investigate today. How does it work? Well, the number of standard atomic orbitals is going to be equal to the number of hybrid orbitals. So if I need to make 4 bonds for carbon, I need to take 4 atomic orbitals, an S, and 3 of those P's. Notice I counted all of the lines. I took an S, a P, and a P. And I hybridized them to make 1, 2, 3, 4 degenerate orbitals. Math has to work out. Whatever you put into the cupcakes, you get out of the cupcakes. And so if I put 4 atomic orbitals in, I will get 4 degenerate hybridized atomic orbitals out. Now, hydrogen cannot hybridize. It only has 1 valence electron and 1 valence shell. So that doesn't work. But what's great about hydrogen is it's usually not a central atom. Hybridization happens for the central atom only. And that's going to be very, very important for us to understand. If we look at a Lewis structure and identify a central atom, that atom can hybridize if required. Usually they do. Very rare occasions, like the H2S example, do we not see hybridization occur. The number and type of standard orbitals, again, determines the number and shape of the hybrid orbitals. So I took an S orbital, this one, and I took 1, 2, 3 P's. I'm going to have an orbital that's some combination of S, P, P, P. Now, that is about 25% S and 75% P. So what my shape tends to look like is kind of like a P with just 1 bloated lobe. And that's because that's what made it. So we take that S orbital, which is the sphere. We took the P orbital, which is the dumbbell, and we literally put them together and make some sort of a hybridized form. Now, when we look at what happens with that hybridized form, here's the S orbital, the px, the py, and the pz. Put them together and spread them all out equally because they're degenerate now, and that's where we get the tetrahedral. Yay! There's much rejoicing. That's where we can get the 109.5. only way to understand how the tetrahedral is formed is through hybridization. We have to have equal energy orbitals in order to understand that. And so hybridization is our theory that predicts what we observe. What about other group 4 atoms? Okay, carbon can hybridize. Can nitrogen? Can oxygen? The answer, yes. Let's think about nitrogen in this molecule, NH3. Nitrogen makes the most number of bonds, so we have hydrogens around it. Nitrogen brings 5 electrons to the table. Each hydrogen brings 1, total of 8 electrons, 2, 4, 6, 8. This is what we would have called the 4-electron group molecule. We would have imagined that nitrogen forms that tetrahedral. Again, you would not need to know how to draw this with the wedges and dashes, but we can kind of emphasize the 3-dimensional shape here. I'm going to put these lone pairs up on top. I'm going to draw a little balloon up here to remind us, yep, they take up space. And there's that 109.5 for the bond angle. Now, how did that actually happen? Well, nitrogen in its orbital diagram had 2 electrons in the 2s and 3 electrons in the 2p. Again, we want nitrogen here to have 4 electron groups. So what are we going to do? We're going to take all 4 of those atomic orbitals. I'm going to abbreviate that AOs. 4 atomic orbitals. We're going to hybridize them to make now 4 degenerate orbitals. I took an S, I took 3 Ps, so I call it sp3 hybridized. Notice that they're a little bit lower than the Ps and a little bit higher than the S's. They're somewhere in between. And then I get to fill up with my 5 electrons. 1, 2, 3, 4, 5. Hund's rule says that I put 1 in each degenerate orbital before I pair. We can predict that nitrogen has a lone pair looking at valence bond theory and makes 3 bonds. All of those 4 atomic orbitals went to make 4 hybrid atomic orbitals, and now we have 4 degenerate orbitals that can go into bonding. So for the sp3 hybridization, it is literally going to be tied to the 4-electron group of Vesper theory. Whenever you have 4 electron groups, you're going to see that tetrahedral geometry. The bond angles are 109.5. That must mean that the actual atom in the center hybridized in an sp3 fashion. Notice the S, the P, and the P. Those are 4 atomic orbitals going to make 4 hybrid orbitals, which is 4 electron groups. Now, what we can do to just describe a little bit more about what's happening is we can actually figure out what orbitals are going into the overlapping themselves. So when we have single bonds are always going to be sigma bonds. You have to have that direct overlap first. So a sigma bond will be the direct overlap that occurs in every single covalent bonded pair of nonmetals. Specifically, what we can say is the carbon that is sp3 hybridized overlapped with the hydrogen that is s orbital. Hydrogen, again, doesn't hybridize. It's an outer atom. Outer atoms usually do not hybridize. When we look over here at the nitrogen, again, nitrogen is sp3 hybridized, and it's overlapping with a hydrogen in an s orbital. So we can say that is true for every single bond in these structures. Now, what about the 3-electron group? I have 2 examples here that I want to go through to be able to emphasize, well, is 4-electron groups the only thing that hybridizes? No, everything technically hybridizes. Let's look at these 3-electron group structures. Carbon's in the middle because he makes the most number of bonds. We've done this guy before, but let's just do him again. Carbon brings 4 electrons to the table. Oxygen brought 6. Each one of those hydrogens brought 1 electron. So therefore we have 12 electrons total. 2, 4, 6, 8, 10, 12. When I look at what my structure has given me, I would say, you know what? I don't want to put that as a lone pair. I want to go ahead and share one more pair so that carbon gets an octet. I ran out of electrons and I didn't have an octet for carbon. So this would be a 3-electron group structure. We would imagine that that is trigonal planar. Carbon has bond angles that are 120 degrees from each other. Again, carbon, well, what happened, dude? You had 2 s orbitals and the 2 p orbitals. If we were to fill those up to get its valence electrons, now we look at this carbon and say he looks different than the tetrahedral. So what happened? Well, in reality, we only needed 3 hybrid orbitals. 3 electron groups, 3 hybrid orbitals are necessary. So I take 3 atomic orbitals into hybridization. I take always an s orbital before a p orbital. Why? Because the s is lower in energy. So what we'll see is a p that's left over, and these 3 degenerate orbitals are called what made them? An s and 2 p's, sp2. I still put 1 electron in each. This energy difference is a small energy difference. We're going to see what's special about that leftover p orbital. It's an ugly way to write difference. So even though it looks like Hund's rule says we should go back and pair, no, we're still going to put 1 in each before we pair because the energy gap between the hybridized and the atomic orbital is very, very small. So with that sp2 hybridized molecule, what we want to be able to think about is that 3-electron group, the trigonal planar system, carbon being the example we just did, which was trigonal planar. If we had a nitrogen that had 3 electron groups and nitrogen was in the central atom, that's what we called trigonal bent. 120 degree bond angles, it's flat. What happened? Well, we only had to take 3 atomic orbitals into the 3 hybrid orbitals. Where is that unhybridized p orbital going to end up? The atom uses hybrid orbitals for the sigma bonds. These will be the 3 sigma bonds. The leftover is that 1 pi bond. Now, the non-hybridized or unhybridized p orbital is where we get the parallel overlap, the pi bond. Let's see a nice image here for our hybrid orbitals. We'll see an image for our pi bond, our unhybridized p orbital, and then we'll go into merging them. Okay, so one S, two P's. Notice that now we are at 33% S, 66 or 67% P. So we're looking a little bit smaller, a little bit bigger lobe here than the sp3. Same basic shape. It looks like a p orbital with an uneven lobe distribution. But that's how these would come together to make that trigonal planar idea and the 120-degree bond angles. Here's where we have our two different types of bonds. Again, the sigma bond is that direct overlap that we talked about earlier. The pi bond is the parallel overlap, now specifically between unhybridized p orbitals. A sigma bond can be unhybridized, like we had talked about with S's and P's, but they also could be hybrid to hybrid or hybrid to s orbital, etc. This is the direct overlap, which was what we called sigma. This is the parallel overlap, which we call pi. Remember, sigma is stronger. It's the holding hands relationship that you get in college. Parallel overlap, the pi, is the not holding hands. The hey, I see you, you're there. It's weaker. It's not going to be directly overlapping. Here's where we can start to see those two different types of bonds. Again, pi bond, hey, high school, I see you. Maybe we stand and talk for a little bit. Sigma bond, now we're actually holding hands. And we have that Venn diagram going on. So we can start to identify the two different types of bonding once we see a double bond. Now here's this molecule that we just did the Lewis structure and 3D shape for. CH2O. One of those bonds, let's make that smaller. One of those is going to be a sigma. Choose one. Doesn't matter which one. One of them, though, is going to be the pi. Whenever you see a double bond, one is that direct overlap right here. Direct overlap, very, very, very strong. That's going to be the carbon sp2 orbital with the oxygen p. Remember, outer atoms do not have to hybridize. They don't need to. Oxygen has two unpaired electrons, so it's good to make its two bonds as an outer atom. When we see that second bond occurring between carbon and oxygen, it can't exist in the middle. It can't exist as that direct overlap. Because remember, electrons repel each other. So if we're thinking about these 4 electrons trying to attract these two atoms together and make a double bond, what we have to be able to imagine is how are they spaced out so that they avoid the repulsion that electrons contain for each other, but maximize the attraction. So we'll always see the sigma bond directly in the center of the two nuclei. And the pi bond, I want us to imagine, is around on the top and the bottom. It's this around feature that makes the pi bond itself. Together, a sigma and a pi make what we call a double bond. Now, a couple of things about that double bond. We said before a double bond is stronger than a single bond. Well, that's because a single bond is simply just a sigma. A double bond is a sigma with a little icing on top, the pi bond. Now, even though the pi bonds are weaker than sigmas, they're additive in strength, meaning a sigma and a pi will always be more strong than just a plain old sigma. What we also see with these sigma bonds is if in a single bond, we have free rotation around this one bond. This can rotate, right? Think about holding hands with someone or just yourself. You can do it with yourself too. There's that free rotation. You can kind of flip your hands back and forth, back and forth. When you have a double bond, there is restricted rotation because of this new bridge on top and the bridge on the bottom. You're locked in place. And so that's going to be something we'll see later on as well. All right, 2 electron groups. Let's continue on. We've done carbon dioxide before. Again, carbon brings 4 electrons to the table. Each of those oxygens brings 6 electrons to the table. So we're looking at 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. But carbon doesn't have its octet, so we're going to share. Again, share. And there's carbon dioxide. Now, when we look at this central carbon, again, we can look at its valence electrons in the 2s and the 2p and identify what do we need? Well, we only have 2 electron groups. We would have called this linear 180 degrees. I'm only going to take 2 atomic orbitals in order to hybridize into my 2 hybrid orbitals. My 2 p's get left over. These hybrids are going to be composed of an s and a p orbital, so therefore they're called sp. I'll have 2 sigma and 2 pi. Every first direct overlap is going to be a sigma. The leftovers, any extra overlap, will be a pi. Doesn't need to be to the same atom. So what we see is carbon has 1 sigma to each oxygen and 1 pi to each oxygen. And so we can look at that central atom carbon and identify he is sp hybridized and has 2 sigmas and 2 pi's. I like this example just to mirror the first one. It's an example where we have 2 central atoms, but it's a simple one, so we're going to try it together. Each carbon brings 4 electrons to the table. Each hydrogen brings 1, so we're at a total of 10 electrons. 2, 4, 6 go into bonding with those single bonds. 8, 10. We don't have enough to reach an octet for everyone. So what we should do instead is form a triple bond. This also is sp2 hybridized. Let's imagine this guy, or sp hybridized. Let's imagine this guy right here. He's got 2 sigmas. And remember, everything else is a pi. So he's got 2 pi's. Even though they belong to the same pair, 2 double bonds in carbon dioxide or a triple bond in C2H2 is going to be a central atom that is sp hybridized. So with sp hybridization, we see that linear shape, 2 electron groups, 2 atomic orbitals are needed to make 2 hybridized orbitals. And so we'll have 2 sigma bonds and 2 pi bonds along that central atom. That formation of the hybrid orbital is 50% s, 50% p. So we're starting to look a little bit more loby on that one side. But again, when they're put together, here's the central atom. I don't want you to think that this is a p orbital when they're put together. It's just that they are have the 2 lobes 180 degrees from each other. Wow. I like this picture because I think it helps emphasize the triple bond itself. So when we look at this triple bond, we see that purple in the middle is the sigma bond. It's the sigma direct overlap of the sp carbon to the other sp carbon. And then when we look at the pi's, notice how the pi overlap is perpendicular to each other. They're 90 degrees because one is a py and one is a pz. And notice also when we're identifying those bonds that are formed by the overlap, this is unhybridized always for a pi. Excellent. Now, where do we get the expanded octets? When the expanded octets occur, it's because the atom is in the n equals 3 principal quantum number for its valence electrons. L can be 0, 1, or 2. So in n equals 3, we have S's, P's, and D's. What that means is we can take up to, in our valence electrons, let's think about for arsenic, we have the 3s, we have the 3p, and way up higher, we do have the 3d. Arsenic is in the third row. It has 3 3p electrons in its valence. Excuse me, 4. Third row and below, but this guy happens to be 4. And what we would need to understand why arsenic makes 5 single bonds is it takes the S's, the P's, and 1 D in order to hybridize into 4 or 5 degenerate orbitals called sp3d. Count them up, 1, 2, 3, 4, 5. And that's where we can put in our electrons and make 5 degenerate bonds. Now, the d orbitals can be used to make pi bonds, but again, we won't really talk about those. Primarily where that comes into play with H2SO4, the sulfur. But again, we're going to primarily look at sigma bonds for those sp3d hybridized orbitals. So even though the d orbitals are empty, they're still available in the valence shell. So there we go. This would be for the 3 guys. If we have 6 electron groups, we need 6 atomic orbitals. We'll take an S, 3 P's, and 2 D's. That's where we get SF6. Again, d orbitals can be used to make pi bonds, but we're going to stick with just the sigma bonds. And there we would see. Take as many atomic orbitals as you need to make the hybrid orbitals based off what you see in the electron groups. So this chart, we should add in this last, or the last 2 columns, the hybridization gets put into this chart really to be able to say, if I know the number of electron groups, yes, I can take the Vesper theory electron geometry. Now I know the hybridization and I know the orbital shapes. So we're really adding to our previous chart there in chapter 5. So for predicting hybridization and bonding scheme, just like before with predicting in Vesper theory, you always have to start with that Lewis structure. You'll get through the Vesper theory to get the geometry around the central atom, and then you'll be able to predict the hybridization based off of the number of electron groups equals the number of hybrid orbitals needed. You can sketch the atom and the hybrid orbitals. What I would want you to be able to do is definitely be able to label a sigma or a pi bond. We'll have some practice in class. Now, here are some problems with valence bond theory. I know, right? It seems great. Why would we have any problems? It has bonding schemes. It expresses bond strengths and bond length and bond rigidity with our single, double, and triple bonds. However, it still doesn't predict perfectly the magnetic behavior of oxygen diatomic. And so, in addition, valence bond theory presumes our electrons are localized in the orbitals, and it doesn't account for delocalization, specifically resonance. Now, when we talk about molecular orbital theory enhancing these issues, we're not going to dive too far into molecular orbital theory for reasons being we just don't have a lot of time to do so, but also it's going to be represented for you in organic chemistry. Valence bond theory predicts many properties much better than Lewis, but again, some issues. What molecular orbital theory can do for us is explain electron delocalization. It applies the Schrodinger wave equation, which we talked about in quantum mechanics, to the molecule setting to calculate a set of molecular orbitals. So it is identifying that, yes, when we have these orbital overlaps, whether they're the direct overlap or the parallel overlap, something happens to create a molecular orbital that we call sigma or pi. And so the equation solution is estimated. You need a very, very big supercomputer to really understand the Schrodinger wave equation. And so there's a lot of math that goes behind this that we are not ready to handle yet in general chemistry. You won't even be able to handle it really ready in organic chemistry. You don't really get to the math and discuss it until you get into physical chemistry, if you're lucky enough to take that class. It's an amazing class, very eye-opening, but it truly is one of those classes that is much later in your chemistry career. So in this treatment, the electrons belong to the whole molecule, so the orbitals belong to the whole molecule. And so there's really this idea that electrons are not localized, they're not staying put in an actual chemical bond, but rather they're moving around the entire molecule itself. From molecular orbital theory, what we have is the linear combination of atomic orbitals. The simplest thing that we can start with is this Venn diagram idea that when two atomic orbitals come together, like the s orbitals, they must create some sort of bonding orbital. We call that sigma, and we do notice that it is energy lowering, right? Overall, the energy difference between the atomic orbitals and the bonding orbital should be lowering. Now, every orbital has two ways to come together, in a constructive way or a destructive way. Just like when two things come together, they can be in phase or out of phase. What we have is a sigma bond, which is favorable. This is called a bonding orbital. We also have a way where they could possibly come together in an unfavorable way, what we call a sigma star. Notice that little star asterisk right there in that top right corner. This is an antibonding orbital. What we notice is that the energy difference with the atomic orbitals and the antibonding orbital is higher in energy. It's destructive. There's actually a node holding those two together. And so when we think about these two options, constructive and destructive, we get into the idea of molecular orbitals. When the wave functions combine constructively in phase, good. Yes, they result in a molecular orbital that has less energy than the original atomic orbital. We designate these sigma or pi. That's what we just described and we talked about and we mapped out in valence bond theory. Most of the electron density is held between the nuclei in those types of bonds. Now, when wave functions combine destructively, the resulting molecular orbital has higher energy than the original atom. That's not good. We don't like that. We call these antibonding molecular orbitals. They're designated as sigma star or pi star. And most of these electrons are then outside of the internuclear axis. There's nodes between the nuclei. Why we have to account for these is so that we can truly understand why some atoms form molecules and why some other atoms do not form molecules. So when two atomic orbitals want to come together, they can be destructive, which is the sigma star, or constructive, which is the sigma. What we want to relate that to is in bonding, the MOs are stabilizing. These are the atoms that actually exist. We'll talk about what that means. We'll go with simple ones, things like the diatomics. Why does H2 exist and not He2? Why does helium diatomic not exist? Well, it's because there are electrons in antibonding orbitals. And so therefore, it's destabilizing. The molecule won't want to form. What we want to be able to talk about here is bond order. Bond order is calculated here. 1/2 of the number of bonding electrons minus the antibonding electrons. If we have a bond order of 0, the bond will not form. The molecule is going to stay as individual atoms, not ever form a molecule. If we have a bond order of 1 or greater, even plus 1/2, anything greater than 0, we will have an actual molecule be able to form. This is where we can start to identify in a molecule whether we have a paramagnetic or a diamagnetic molecule. Now we're going to see MO diagrams similar to what we had for atomic orbital diagrams, AO diagrams. We can look at molecular orbitals, sigmas, pi's, sigma stars, pi stars, and be able to say, let's build them up from the bottom, right? We'll off-bow principle those, and we'll do Hund's rule, we'll do the Pauli exclusion principle, the exact same way that we built up our atomic orbital diagrams. We can do now with our molecular orbital diagrams. And now with this molecule, we can say, is it paramagnetic or diamagnetic? That will help us with our observations of things like oxygen diatomic. So when two atoms come together, we got one orbital on the left, one orbital on the right. We will always make two molecular orbitals, just like before, math. We put 2 in, we get 2 out. One is favorable, one is not favorable. And then we get to fill up from the bottom. Now this region right here is my new molecular orbital diagram, right? This is where I get to say, if I have 2 electrons, I get to start from the bottom and build up. Now I get to put 2 electrons in each. So I get to put my 2 electrons down at the bottom, and nothing has to go in the antibonding orbital. I look at bond order for H2 and I say, there are 2 electrons in a bonding orbital, this one, and I have no electrons in my antibonding orbital. And so 2 minus 0 is 2, multiplied by 1/2. The bond order for H2 is 1. Therefore, H2 exists. So why doesn't He2 exist? Well, I still have the same sigma and the same sigma star, but now I have 4 electrons. 1, 2, 3, 4. So I start at the bottom, 1, 2. I gotta move up into the antibonding orbital. And therefore, what I see is the bond order for helium diatomic is 0. So helium diatomic does not exist. Now, what about He2 plus 1 cation? We do know that alpha particles are really just He2 plus 2. So He diatomic can technically form, but it has to be in a cation state. So let's see, would the +1 cation form? That would only be 3 electrons, 1, 2 from one atom, and a third from an He+1 cation. We fill up our MO diagrams, we do our math. Yes, it exists. Just by having more bonding electrons than antibonding electrons, our molecules can exist. So the bond order is an important concept to be able to utilize so that when we look at a theoretical molecule, we can start to explain, does it exist or does it not exist? So MOs are a linear combination of atomic orbitals. The total number of MOs formed is always going to be equal by the number of atomic orbitals that it actually came from. So 2 atomic orbitals go in, 2 molecular orbitals have to come out. When assigning the electrons of a molecule to the MOs, we fill the lowest first, Aufbau principle. We make sure we follow Hund's rule, right, with degenerate orbitals. We'll see those in a second. And then we can also make sure we follow the Pauli exclusion principle with only 2 electrons in each MO. Now, the bond order of a diatomic is the number of electrons in bonding minus the number of electrons in antibonding divided by 2. Stable bonds require a positive bond order, more electrons in bonding MOs than in antibonding. Another way of being able to look at bond order is simply by understanding the number of bonds the 2 atoms made. So we can look at bond order for non-diatomic things. A single bond will always be a bond order of 1. A double bond will be a bond order of 2. A triple bond will be a bond order of 3. When we want to use MO theory, we would use our math, right? If we wanted to just look at bond order for a bigger molecule, molecular orbital theory is very complicated. So we can use this simplistic relationship. I want to go through one more example of utilizing that MO diagram. Again, this MO diagram would be something that you would just have to fill in for. Now, H2 diatomic exists. What about H2 anion? Well, hydrogen normally brings 1 electron to the table. What if one of those hydrogens was a hydrogen anion and brought 2 electrons? So we have 3 electrons total to fill up in the red portion of our MO diagram. Again, we start from the bottom, 1, 2. We got to move up to put that third one in the next orbital. Bond order would be 1/2, 2 electrons in the bonding, 1 electron in the antibonding. Yeah, hydrogen diatomic anion does exist. But guess what? It's weaker than the normal H2 diatomic molecule. Why? Because the bond order is lower. The higher the bond order, the stronger the molecule's bond is. Therefore, the more stable the molecule. Now, when we have other diatomic molecules, we can still use the same s orbital to sigma bonding s orbitals and sigma star s orbitals. These are the simplistic ways of viewing the MO diagrams. We could have, though, an interaction of p orbitals. So when we get into the second row diatomics, such as carbons, nitrogens, oxygens, and fluorines, what we want to be able to imagine is a sigma bond created with 2 p orbitals. Again, there's a bonding and an antibonding in the 2px, the 2py, and the 2pz. So what actually happens is we create this beautiful molecular orbital diagram. You would not need to memorize this, but you should be able to identify here are our molecular orbitals I'll highlight what atoms they're for. When we start looking at the atoms in the P block. Now specifically, notice the difference between moving from boron to nitrogen all the way over to the molecular orbitals of oxygen, fluorine, and neon diatomics. Notice the swap of the sigma and the pi. Now, again, you would not need to understand why that happens. You would just need to be able to fill this up and be able to explain, does the molecule exist? So here's where we start to look at our orbitals and our bond orders. All of these diatomics do technically exist. Boron diatomic, carbon diatomic, nitrogen diatomic, oxygen diatomic, fluorine diatomic, except for neon diatomic. Why does neon diatomic not exist? When we fill this whole orbital diagram, we see it ends up with a bond order of 0. And so MO theory is a much better way to organize our thoughts of looking at the expectations, does the molecule exist or not, and what does the molecule actually look like in three-dimensional space? How does the shape occur? This is where we will end our discussion of Chapter 6. Thank you so much.